Hey everyone, and welcome. So, have you ever stopped to think about how a machine actually learns to make a choice? How it goes from a bunch of data to a real decision? Well, today we're going to pull back the curtain on one of the coolest tools in machine learning, the decision tree. It's surprisingly simple, but also incredibly powerful.
So let's just start with the big question, right? How does a machine, just a chunk of code, learn how to guess something? Whether that's figuring out what type of flower you're looking at, or if a loan application is a good risk. How does it get from raw data to a smart guess?
Well, the answer is kind of funny because it's something you definitely already know. The machine basically learns by playing a game. A guessing game you probably played on long road trips as a kid. 20 questions. It just asks a series of simple questions to narrow things down one by one until it lands on the most likely answer.
All right, so let's dig into that idea. The guessing game. What is a decision tree? This whole approach, making decisions by following a logical path of questions and answers, is the exact idea behind a decision tree.
Okay, so what is it really? When you strip everything else away, a decision tree is just a flowchart. Seriously, that's it. You start with some observations, some data, and you just follow the branches based on a series of yes or no questions until you land on a final conclusion. It's a beautifully simple concept.
And to really get it, let's look at the parts of a tree. It all starts at the top with the root node. You can think of this as your entire big pile of data, all mixed together before we've asked any questions. From there, you have the branches, and each branch is just a question. Answering that question leads you to an internal node, which is just a new, smaller, more sorted group of your data. You just keep repeating that process until you hit the end of the line, the leaf nodes, and those are your final answers.
All right, so we get the structure, but the real magic, the part that feels like actual learning, is how the machine builds this thing from scratch. I mean, how does it figure out which questions to ask and in what order to get the best answers? This part is really clever.
To make this real, let's use a classic famous dataset called the iris flower dataset. The mission is simple. We want to build a tree that can look at a flower's petal length and width and correctly guess its species. We've got measurements from 3 different types of these irises.
So put yourself in the algorithm's shoes for a second. You've got all this data. What's the single best first question you could ask to start sorting these flowers into cleaner piles? You could ask about the length or the width, but which question is going to give you the most bang for your buck?
Well, this is where the computer shines. It crunches all the numbers, tries out all the possible questions, and finds the single most powerful one to start with. And in this case, is the petal length less than or equal to 2.45 centimeters? And boom, just like that, with one simple question, it perfectly separates all the Setosa flowers from the other two. What an incredibly efficient first move.
This whole process has a fancy name, recursive partitioning. But don't let that scare you. The idea is simple. It's what we call a greedy approach. That just means that at every single step, the algorithm isn't thinking 5 moves ahead. It's only focused on finding the best possible question to ask right now to split the data it's looking at. Then it splits the data and does the exact same thing on the 2 new smaller groups. It just repeats this over and over until the groups are pure, which just means they only have one type of flower in them.
But that leads to a really important question. How does it know what a good question is? What makes one split better than another? Well, it all boils down to this idea of measuring purity. The goal is to ask questions that make the resulting groups as pure or as unmixed as possible.
The most common way to measure this is with something called Gini impurity. Now, don't worry about the math here. The concept is really easy. Think of it as a mixed-upness score. A score of 0 is perfect. That means every single item in that group is the same. The higher the score, the more chaotic and jumbled up the group is. And this is what that looks like in practice. The algorithm is always hunting for a good split. That's a question that takes a mixed-up group and creates 2 new groups that are much, much purer. It causes a big drop in that Gini impurity score. A bad split, on the other hand, is a question that barely helps. You ask it, and the new groups are still almost as jumbled as when you started.
So, as you can see, decision trees are awesome because they're so intuitive. But, and this is a big but, they're not perfect. Like any tool, it's super important to understand both their strengths and their weaknesses.
Okay, so their biggest strength, their superpower, is that they are a white box model. Unlike a black box where the logic is hidden, you can look at the flowchart and see exactly why it made a certain choice. But on the flip side, they can suffer from a classic problem called overfitting. That's where the tree gets too complex and basically memorizes the training data instead of learning the general rules. They can also be a bit unstable, where tiny changes in your data can sometimes create a completely different tree.
But even with those weaknesses, their simplicity and the fact that you can explain them make them incredibly useful out in the real world. So let's talk about where people are actually putting these models to work.
Oh man, they are absolutely everywhere once you start looking. In medicine, a tree can help a doctor assess a patient's risk by asking a series of questions about symptoms and tests. In banking, they're the workhorse for deciding on loan applications. Marketers use them all the time to classify customers into different groups for ad campaigns. You see them in manufacturing, in almost any industry you can think of.
And this is maybe the most important takeaway. Understanding decision trees is crucial because they're not just a standalone tool. They are the literal fundamental building blocks for some of the most powerful and popular machine learning models out there today, like random forests. A random forest is basically just a whole team of decision trees working together to make an even smarter prediction.
It all comes back to this one simple idea, which is summed up perfectly here. The great thing about decision trees is that you can actually see what they are doing. You can trace the path. You can explain the logic. In a world of incredibly complex AI, that is a huge, huge deal.
And that leaves us with a big question to chew on. As AI gets woven deeper and deeper into our daily lives, making more and more decisions for us, how much should we value being able to understand its reasoning? You know, in a world full of these mysterious black boxes, maybe, just maybe, the most powerful tool of all is the one we can actually understand.